Hey there, Mr. Sutton here, bringing you the Pre-Cal Honors 4-7 lesson on applications of exponential equations. In this one, we will be setting up and solving exponential equations for some real-life situations, including, let's see here, how old something is, and also there's another one in there dealing with interest. For our first example, we want to figure out how long it takes $250 to become $2,000 if invested at 6% interest compounded continuously. So pause the video and see if you can write an equation to describe this situation. All right, let's see how that went. So this is the most important part, really, is getting this initial setup. So we're going to start with the formula f of t equals PERT, P-E to the RT, because this is our continuous compounding formula. Let's plug in everything we can for this now. So we are starting with $250. That's our principal. That's our P. The rate is the 6% here, 0.06. The time we don't know. We're trying to figure that out, how long. And you might not know what to do with this 2,000, so we'll just kind of punt that until the next step. So right now we've got f of t equals 250 times e to the 0.06t. Now at this point we want to figure out not what the money's going to turn into after a certain amount of time. That would be the normal way of doing these back a few lessons. Now we want to know how long, what t value will give us an output of 2,000. So at this point, we have to take our target amount, the 2,000 here, and plug that in for f of t. So we're going to write 2,000 equals 250 e to the 0.06t. And if you didn't get this far, well, start here and see if you can go ahead and solve the rest of this. All right, so to start this off, we have to isolate the exponential term. We'll start by dividing by 250 on both sides. That gives us 2,000 over 250, or you could reduce that to 8. And now we have to take the log of both sides, since I don't know what power of e 8 is. Now, as a little bit of a shortcut here, since we're dealing with e, you can actually save a little bit of time if you use ln for e instead of using normal log. We're going to have ln of 8 on the left side, and on the right side, we're going to have 0.06t popped out times the ln of e, but the ln of e is really just 1. So this is just ln of 8 equals 0.06t, with an invisible ln of e that we don't have to write over here. Next, to get t by itself, I divide by 0.06, and I need to do this on the calculator now. So doing ln of 8 divided by 0.06, we end up with about 34.66 if we round off to 2 decimals, and that is going to be years. We'll do one more example, slightly different type of problem. The Mona Lisa is stolen from the Louvre. This actually happened at some point. Weeks later, another museum buys a Mona Lisa. Carbon dating shows the canvas has 97% of the normal level of C14, which has a half-life of 5,700 years. How old is the canvas of the painting that was just discovered? And is it possible this painting is authentic? So pause the video and see what you can get for the setup on this one. All right, so to get started here, we have half-life involved, so I'm going to write the half-life formula. F of t equals ab to the t over k. Let's fill in what we can initially here. So we know that we have a b value of 1/2 or 0.5 because we're dealing with half-life. We have a k value of 5,700. That's how long it takes before we apply that 1/2. The thing that we're trying to find is the t value. And you might be a little confused about what the a value should be. So on this one, we're starting with 100%, and we're trying to figure out how long it takes that to become 97%. So I'm going to write in 1 for a, because 1 is equivalent to 100%. So if we're trying to figure out what our target amount is, we're trying to figure out, again, when 100% becomes 97%, I'm going to rewrite 97% for f of t as 0.97. So this is the equation I ultimately need to solve. And I'm not going to write this 1 again because, well, 1 times anything is just itself. But it is there. All right, if you didn't get this far, that's fine. Pause the video and try to take it the rest of the way. All right, so this one, just like the last problem, we're going to have to use logarithms. No point using ln on this one, but you could if you wanted to. It actually doesn't matter whether you use normal log or ln for any of these problems, unless there's an e involved. So I've got the ln of 0.97, or the log of 0.97, either way. Over here I've got a pop-out value of t over 5,700 times log of 0.5. And then solving for t, multiply by 5,700, divide by log of 0.5. We end up with this situation here, and now it's time for the calculator. For this one, just to keep things sorted out, I'm going to go alpha y equals and n over d to get my fancy fraction form. We've got 5,700 times log of 0.97, all of that divided by log of 0.5, and enter. Rounding that off to 2 decimals, that's about 250.48, or roughly 250 years. So is it possible that this painting's authentic? Well, 250 is pretty old, but is it old enough to be the real Mona Lisa? You might know that the Mona Lisa was painted by Leonardo da Vinci, who lived roughly 500 years ago. So yeah, this is not quite old enough to be the real thing. Probably, almost certainly is a fake. Now, even if this were over 500 years old, it might have just been something one of Leonardo da Vinci's contemporaries just copied from him. It still could be a fake, but this is definitely a fake. So that's it for applications of exponential equations. Until next time, see you later, Mona Lisa.